So here I'm just going to take a quick break between our videos to give you essentially what I'm thinking is going to be my very simple and basic crash course in matrices. Now matrices are a big topic and it can get pretty complex, but here I'm just going to show you a few simple functions that are going to help in our future lessons. It's only going to be used in a couple of places, but I find these functions can often be really helpful. And like our quaternions, you won't really need to understand matrix math to be able to use it in our setup. So in terms of what a matrix is, you can think of it as a 4x4 grid of decimal numbers, or 16 floating point numbers arranged in a grid. And these numbers are a very compact and efficient way to store a transformation. So in the same way that we can put down a transform SOP to transform some geometry in Houdini, we can also store that transform as a matrix attribute. So as a quick example, let's put down our rubber toy model to demonstrate this. I'm going to turn off our shader here. Let's take a transform SOP and apply that to adjust our model. So we're going to grab that, get our handle, just move over here up a little bit, let's rotate it around, maybe scale it in a little bit, just sort of place it somewhere like this. So we've moved it, but at the bottom here you can see we can also save this whole transform we've created up here as a matrix attribute. So if we do output attribute, you can see we can store this as xform. So if we come to our attribute spreadsheet, just right click and choose spreadsheet. It's a detail attribute, so rather than being stored on each point or primitive, it's just stored once on our geometry under detail. And this is just an attribute with 16 float digits down here, which are essentially those 4x4 grid of numbers just spaced out here in a line. Now, as with quaternions, the numbers are hard to really understand, but again, we don't really need to worry about that because we're never going to be setting these numbers ourselves. So rather than using our transform SOP itself, we could also instead multiply our point positions of our original rubber toy by this transform matrix to do the same thing. So I'm going to put down a point wrangle here. I'm going to connect our model to the first input or 0 input, and I'm going to connect our transform, which has our matrix attribute stored on, to our second input, which is our input 1. So on the point wrangle, let's just create a matrix variable just by typing matrix M. It can be called anything you like, but M is a good sort of convention. And let's grab the matrix from our transform just by using the detail function. So we're going to type detail. We want to grab it from our first input port. So this is 0, this is 1, this is 2, this is 3. So let's grab it from input port 1. It's called xform, so we just put that in quotes, xform, and we just put 0 afterwards. So we've stored this as a variable. So let's now apply this matrix to our points. So we're going to type attribute P for our point position times equals, so that's our current point is going to be itself times our matrix. And if we view that, you can see it's now moved into exactly the same position. So essentially it's done exactly the same thing as this. It's just taken our transformation as a matrix transform, and then we've multiplied that with our points here. So matrices are another way to combine transformations and apply them to our geometry. So going back to our picture here, just as a bit more info, even though these numbers can be any value, there is order to their arrangement. So this top left group of 3x3 actually stores the rotation and the scale. The diagonal of those 3x3 does the scale, and all 9 numbers do the rotation. It's a little bit hard to think of. It's kind of like you're combining two things with one set of numbers, but yeah, essentially the diagonal is the scale and all 9 of those are the rotation. So these 3 numbers to the right of that are our translate X, Y, and Z, And the other numbers at the bottom, we don't really need to worry about. They're more to do with offsets or when you're combining matrix transformations. So just know that the full combination of these 16 numbers can do any transformation on our geometry. As well as a 4x4 matrix, there's also a subset of this called a 3x3 matrix. I don't know if we'll use this in this course, but you can use this as well sometimes. And this is just the top left box. So with this one, you can only do scale and rotate functions. But if you have the full matrix, which is a 4x4, you can do translation as well. We don't need to know this all for now, but it's just a bit of context into what the numbers mean. So one last thing here that's useful to know is the numbers I've put here with the zeros on the diagonal, the ones on the diagonal and the zeros everywhere else is a special kind of matrix called the identity matrix. And this one is important because we'll often start by creating this as it does nothing to our geometry in terms of transformation. And then we can apply our rotations and scales to this. So the identity matrix is kind of the same thing as adding a default transform SOP with no translation, scale, or rotation. So let's now look at how we can set up our own matrix and how we can adjust our geometry with it. Okay, so I'm going to put down a grid. Dive inside, let's reduce our size a little bit so it's a little smaller. And I'm going to put down a point wrangle afterwards. Let's create a matrix variable. So matrix is the type. Again, we're going to call it M, and that's going to be equal to ident. And ident will return the identity matrix. So it's just a matrix with nothing applied in terms of position, scale, rotation. We can now multiply our position by that. And as we'd expect, it's not going to change anything at all. So let's now rotate our matrix to create our first transformation. We can put down the rotate function, and this will apply a rotation to our matrix. If we look at our second declaration of the function here, you can see it's going to rotate our matrix by an amount. So that is like degrees around, and then an axis. So that's going to be the axis. So if we were rotating, say in Y by an amount, we'd be rotating, this would be our Y axis, we would be rotating around here by a certain amount. So let's try this out. Let's put our matrix M for the matrix. Let's make a channel float slider, and this will be the amount we're going to rotate. So let's call this rotate. Let's put down an axis. It's a vector, so let's do channel vector. Let's call this axis. Close out the quotes. Close out those and close out the semicolon. Let's create this. Now the weird thing about matrix functions is you would expect, sort of typically from Vex, that you would type M equals rotate M, but with matrix like functions like this, you actually just call them like this. So the rotate function actually applies the rotation to the matrix in memory. So you just need to put it like this and it will apply it. Okay, so let's maybe set this to be 1 in Y, and we can rotate. Now one thing we need to remember is I want to rotate this in degrees. Houdini works in radians, so let's convert that a second by typing radians. Let's put that in brackets around our channel float. So now we're converting from degrees to float. And let's also come up here and just edit our parameter interface. And let's set our rotate to be between 0 and 360. So 360 degrees. And the other thing we want to do as well is normalize our axis. Again, because it's an axis, we need to make sure it's got a unit length of 1. So let's type normalize, open brackets, and close out that. So now we can rotate around our y-axis. We could, of course, come across and rotate around our z-axis. We could even combine these together and maybe rotate around our Z and Y axis, like so. Now this is a good reason why you want to normalize this. In this case, I've set 2 axes to 1, so the unit length is going to be greater than 1. Now in the case of this, it's fine because we've normalized this, but if we didn't have this normalized, if I just remove that, you can see we're now getting some really weird translations, so it's kind of skewing it while it's rotating. So if you ever see this, it's probably a sign that you've got an axis that hasn't been normalized. So just to be safe, it's always worth just putting this around a normalized function. And I'm just going to set that back to be Z for now, so we can rotate like this. Cool. So as well as rotate, we've got other functions. We could use translate. I don't use this too much, but translate, let's just put in curly brackets to create a vector here. Let's go x0, y 0.5, comma 0 again. So we're creating a vector, just 0.5 in the y. And you can see we've now translated our points 0.5 up. We could also use a scale. So we can scale our matrix by, say, 0.5. And now we've scaled all our points in. So it's kind of the same as just setting uniform scale to 0.5. So I'm going to delete this for now and just stick with our rotation to show the next bit. So this variable here is per point. So we can also vary this transform per point. We could make a mask that goes along our geometry and rotate by this. Now, a very useful function in Houdini is relative point bbox, and this creates a vector on our point positions based on our bounding box. And we can use this like a mask. So let's come up here. Let's create a vector called mask. Let's call rel point bbox. You can see it there. Just click on that to complete. Press enter. And this really just needs a geometry and a vector position. So our geometry is just our current geometry, so it's 0 for the 0th input. And then for our point position, or our vector position, we're going to type attribute p. So we're going to use our current point position here. So this has now stored this relative point bbox mask inside our points. And we can visualize this by typing attribute cd equals mask, just to send that to the color and see what it looks like. So we get this nice gradient here. And if I was to say, just take the X component of our mask, so the X part, you can see we've got a black to white value running across the X of our geometry. If I set this to be Z, you can see we've now got that running across the Z axis. You could set this to Y, but for a plane it makes no sense because there's no thickness, so everything's the same. For now, let's just set that back to be Z. So I'm actually not going to set the color. Let's just ignore that for now. But let's in fact multiply our mask Z by our rotation. So if we were to put multiply by mask dot Z, you can see we're now actually kind of twisting our geometry like this. So points where the mask is 1 get rotated by full amount. Points where the mask is 0 don't get rotated at all, and everything else in between is interpolated. So we've almost created like a twister former here. So that's pretty cool, pretty interesting. The other thing that's even more interesting is that you don't have to just transform your position. You can actually apply this to any vector attribute, such as maybe our normal or even a velocity. So let's give our grid some normals. Let's put down a normal SOP. Let's create point normals, and let's enable our visualizer here. So instead of rotating our position, let's just rotate our normals. Again, it's just a vector attribute, so we can rotate it by a matrix. Now you can see this looks kind of weird because we're rotating our normals, and that in turn is messing up our surface normals, so the display goes a bit crazy. If I just tap W to go over wireframe, you can probably see a little bit easier that we're now rotating our normals around by this. This is the thing I actually use a lot Once you can rotate normals, it makes for another convenient way to align things. We could put down a copy to points and align our instances based on this normal. So I find this is a really cool way to sort of adjust things around geometry and twist things based on normals. So it's a useful one to know. I mean, you could even rotate your colors, for example. It doesn't really make sense, but it's still an interesting idea. If we were to put, say, switch back to our normal view, let's put down a color SOP here, set it to be white. Let's now make our CD to be rotated by the matrix. And if you do this, you can see, look at that. Pretty cool. I'm sure you could use this for something. To be honest, you don't normally want to rotate your colors by a matrix, but again, it's just a vector attribute, so it can be rotated in that way. Okay, so let's just set that back to N for now. In fact, maybe P. And we've got our rotation here. So this is actually the same thing as what transform SOP does internally anyway. So it would create a matrix transform based on what you've set up here, and then it applies that to all the attributes here. So you can see it currently it's applying, let's just do a rotation. So it's applying this to everything, in particular our normal and position. So it's rotating our normals and our point position. You could, of course, just set this to be P. So you're just rotating your position, but not your normals. You could just set it to be N. And then it's now rotating just your normals and not your position. And if you set it to be everything, it's just going to rotate everything. It doesn't rotate your color because you don't normally want that. So it's quite clever in that it doesn't do your color, but So that's also another way you can rotate things. But the nice thing is if you use these functions here, you can rotate things based on sort of masks or fall-offs or things like that. I think that's about everything. Let me think. There is also one thing is you can see by default when we rotate our geometry with our transform, it's doing the position and the normals. Of course, when we do ours and we're twisting this, we're actually just rotating our point positions here. You can see the normals aren't moving. And the reason for that is we need to also rotate our normals if we want it to do the same thing. So we need to do attribute N times equals M. And now, because we're doing both of them, we just have to sort of specifically tell it to do both, whereas the transform SOP will do everything by default. Okay, I think that's everything. This was a little heavy maybe, but we'll be using this stuff a little bit in the next few lessons. The important thing to remember is just these functions here. So we've got our ident function, which creates our identity matrix. We can then use rotate to rotate our matrix by a certain amount on a certain axis. And then we use this to basically apply or multiply our points or our normals by our matrix. I hope that made sense. I didn't want to get too deep into it. Already I feel like we've gotten into some pretty heavy territory, but certainly the whole idea of being able to rotate normals for me is something I use a lot and I think can be quite a useful thing to have in your toolset.